Good day and welcome to Math 111H Calculus 1 Honors, The Joys of X. Today we're going to discuss curve sketching and about how derivatives can influence the curve shape and how we can use derivatives to sketch curves. So let's review for a moment that the first derivative of a function gives us the slope of a curve. Therefore, the second derivative of a function gives us the slope of the slope. What does that mean? The first derivative gives the rate of change of f. The second derivative gives the rate of change of f prime. So the second derivative gives us the rate of change of the slope of the curve. What we're going to discuss in today's lecture is how knowledge of the first derivative and the second derivative, and just whether the first derivative is positive or negative and the second derivative is positive or negative, how just that knowledge can help us analyze and understand and sketch curves. First, we need to discuss the idea of increasing and decreasing. If x is moving to the right, if we're moving to the right along a curve and the curve is moving upward, we say the curve is increasing, or f is increasing. If the function is going down as we move to the right, we say that the function is decreasing. So moving up as we go to the right, well, that's the same as saying the first derivative is positive. If the first derivative is positive, the slope is positive. So the function, therefore, is increasing as we move to the right. And we can use the mean value theorem to prove this. If x2 is to the right of x1, then x2 is bigger than x1. So x2 minus x1 is bigger than 0. And we can note that the derivative somewhere between x1 and x2 is equal to the slope of the secant line from x1 to x2. We can bring the x2 minus x1 to the other side, and we find that f of x2 minus f of x1 is x2 minus x1, which is positive, times f prime of c, somewhere in the middle. And if the first derivative of the function is positive on the interval, then this is also positive. So therefore, the expression on the right is positive. And therefore, f of x2 minus f of x1 is positive, and f of x2 is bigger than f of x1. So if the slope of a curve is positive, then as we move to the right, the values get higher. Similarly, if the slope of a curve, if the first derivative is negative, then the function is decreasing on the interval. Now let's discuss the first derivative test. We discussed last time the idea of a critical number for a function f of x. Critical number is a value c where the first derivative is 0 or that the first derivative does not exist. Now we know for functions that the only places that functions can cross 0, that the value of a function can change from negative to positive or from positive to negative, is when the function crosses 0 or when the function does not exist. Well, that's going to be true for derivatives as well, that the derivative of a function can only cross from negative to positive or positive to negative when the derivative is equal to 0, or if we have some sort of a discontinuity going from negative to positive or vice versa. So if the derivative of a function changes from being positive, so going up, increasing, to negative, going down, then in between one has to have a local maximum. You're going up and you're going down, so you have a local maximum. If the derivative of a function changes from being negative, going down, to being positive at c, then f of x has a local minimum at c. If the derivative does not change sign at a critical number, so for example, the derivative is equal to 0, then you might have that the function's increasing to the left of c, levels off at c, and then continues going on up. Here are some examples. On the left, we have f prime of x is greater than 0, so the slope is positive. On the right, the slope is negative, and so in the middle, we are at a maximum. Similarly, in the curve on the right, we have that the slope is negative, f prime of x is negative, and then f prime of x is positive, and so in between we have a minimum. Let's discuss what the second derivative can tell us about the shape of a function. Well, since f prime of x greater than 0 means that f of x is increasing, meaning if f prime is positive, then the function's increasing. Then if f double prime is greater than 0, f prime is increasing. What does that mean? That means if the second derivative is positive, the slope is getting more positive. So if the slope is already positive, it gets even more positive. If the slope is negative, it becomes less negative because the slope is increasing, becoming more toward the positive end. So if f of x is increasing and the second derivative is positive, then it starts increasing even faster. That's on the right portion of this curve. That if f of x is increasing, it's going up even faster as we move more to the right. If f of x is decreasing and the second derivative is positive, that means that the slope is getting less negative, right? F of x is decreasing means the slope is negative, but the rate of change of the slope is getting positive, so the slope is getting less negative. The curve is leveling off as we move to the right. So although the slope stays negative, it's less negative. The slope is more toward the positive. So when f double prime of x is positive, that is when the second derivative is positive on an interval, we say that f of x is concave up on the interval. And we'll have the shape of this kind of a curve, like a smile. Concave up has the shape of a smile. So even the left portion is considered concave up. The right portion is considered concave up. Any piece of this is considered concave up. Now, let's consider the case where f prime of x is negative, right? F prime of x is negative means that the function is decreasing, and so the second derivative being negative, what does that mean? That means that the rate of change of the slope is negative, and so the slope gets more negative. If f prime of x is negative, if a curve is decreasing and then the second derivative is less than 0, it means that the function is decreasing ever faster. So that's the right portion of this curve. The function is decreasing and it's decreasing even faster and faster. If the function is increasing and the second derivative is negative, then the function increases more slowly, right? Because the second derivative is negative, and that means that the first derivative is going down. It means that the slope is decreasing. So we have the function's increasing, but the slope is going down. It's becoming less positive over here. And we say that when the second derivative of a function is negative on an interval, that the function is concave down on that interval, kind of on a frown. So the slope of the curve as we move to the right is getting more negative. First the slope is positive, but then it's less positive, the slope is 0, and then it becomes negative and more negative. Second derivative being negative gives us that shape, concave down. We also have the concept of an inflection point, and an inflection point is a point along a function where if the function is continuous and the curve changes from concave up to concave down, or vice versa, then we call that point where it changes concavity an inflection point. So on this curve, we have a concave down region on the left, we have a concave up region on the right, and the point at which it changes from concave down to concave up, that's called the point of inflection. And in this case, it's at 0, 0. So we also have a second derivative test that helps us understand local maximums and local minimums. If the second derivative of a function is continuous near a point x equals c, and if the first derivative is 0, so that means if the slope of the function is 0, but the second derivative is positive, well, it means the curve is flat, but we're on a smile. Curve is flat, but on a smile means that we must be at a minimum. If the slope is 0, but the second derivative is negative, meaning we're on a frown, the curve is concave down, then we must have a maximum. The slope is 0, so the curve is flat, but it's concave down, so therefore we must be at a maximum. So using the second derivative, or checking the second derivative at a point where the first derivative is 0, can tell us whether we're at a local maximum or at a local minimum. Jaime Escalante was a great teacher at Garfield High School in Los Angeles, and his work was publicized in the movie Stand and Deliver. He told of an amusing incident at the school. He said, "I had just caught a student copying from another student. So I promptly gave the copying student a 0 on the test. The student complained that I didn't like him, and that was why I gave him a 0 on the test. The student called his mother, and we had a conference. The mother said, 'You don't like my son. That's why you gave him a 0. I responded, 'Ma'am, he was cheating.' The mother said, 'My son? My son would never cheat. Do you have proof?' I responded, yes. Let's take a look at your son's paper, and let's take a look at the other student's paper. The other student's exam on question 1, the answer was 14. Your son's answer was 14, and that's the correct answer. So the mother said, well, how can you tell that my son cheated? They both got the correct answer. So I went on to question number 2. The other student's answer was 6. Your son's answer was 6, and that's also correct. Again, the mother says that, look, how could you tell who cheated or if anybody cheated? So I said, let's look at question number 3. The other student's answer, I don't know. Your son's answer, me neither. Thank you for joining us today. Have a great day, and may the power of math be with you.